Yeah. Okay. Our last lecture for today is actually two lectures about effective spin forms. The first part will be done by Haggard, who's professor at Bard College, and the second part is done by Seth Azant. Yeah, and I think you will switch in the middle then.
Yes, thank you so much, Johannes. Thank you, everyone, for being here. It's a pleasure. I'll make the same request as Carlo. It's difficult to speak to a field of black screens. So if anybody is willing to share video, I would be delighted. It makes a big difference for the speaker to have some sense of reaction. And the other opening comment I'll make is that I'm a huge fan of questions as a way to learn. I think it's the tool par excellence. So please don't hesitate to unmute and ask questions in the chat, however you like. I really don't mind at all. It's a delight. I want to build most closely on the lectures of Maite Dupuy. Maite presented spin foam models, the covariant approach to quantum gravity. And this is a sort of supposed to be an advanced lecture reporting a bit on recent research in this area. And so I'll take that seriously, or rather Seth will take that much more seriously and give you a real overview of many results. And I'll try to build up enough background so that you can understand where all those results came from. So I will try to start really at the bottom and how do these spin foam models work, and then we'll build up from there, and Seth will give you a review of results. This is joint work mainly amongst these four collaborators at the moment. Myself, Seth Asante, Bianca Dietrich was the lead who got us all started, and then Jose Padua Arguez. And the first two papers were primarily Seth Bianca and myself, and the last paper referenced here is Seth Bianca and Jose. And in that last paper, they made big strides in treating the theory from a Lorentzian perspective. So treating both space and time. Up to that point, we'd been largely working on Euclidean quantum gravity, where you treat time as another spatial dimension. I'm going to throughout kind of give you previews of the Lorentzian case, but Seth will focus more on the Lorentzian case, and throughout I'll use the Euclidean case to help you try and build intuition. It's slightly simpler, and I think it'll help. Uh, Most importantly, we'd love to invite all of you into this research. I think it's very accessible. It's a place where students could really get going quickly. And so one of the ideas that we had, the school can only provide 2 hours for this because it's sort of a special topic lecture, but we'd love to go through a numerical example with you. It would be using Mathematica, and you would just take the code that we've already written, and we can go through it together. So later this week, probably tomorrow, we'll send out a survey asking if anyone's interested, and we can do these numerical labs next week. This is independent from the school. It's just these four collaborators who are putting it together for you to get a chance to try and use the code. You're more than welcome, and we'll probably try and break it up into smaller groups that each one of the four of us would work with to give you a little bit more personalized attention. So that's the plan. Um, Let me tell you very quickly what an effective spin foam is. It's a whole family of different geometrical path integrals for quantum gravity. So the word effective is being used here in the sense that they provide a spin foam model with a very efficient computable dynamics. One of the challenges we faced a lot in quantum gravity is the putting our models on a computer and getting simulated results out of the computer. So effective spin foams are very well designed for this. The models have already been used to recover discrete gravitational dynamics on a truncated triangulation. So we're not modeling some huge space-time, we're modeling, just a few simplices glued together to give a very small number of gravitational degrees of freedom, but we're successfully getting the gravitational dynamics you would expect in a semi-classical regime. So this is very exciting. I think these are new results that the community is getting interested in. The name effective is supposed to carry a second connotation, which is that it's really a family of models. So I'm going to tell you a lot about how we glue different parts of our space-time geometry together today. And by choosing different gluing constraints, you can get different spin foam models. So for example, the EPRL FK model that Maite told you about is going to be within the family of effective spin foams for a particular kind of gluing constraint. I'm not going to treat that one yet, partly because we haven't discovered what that gluing constraint is yet. So that's open research. But I'm going to treat a simplified version, and you'll see the details of that. I want you to notice up front that sometimes the word effective is used as an approximate, approximate quantum field theory or something like that. And that doesn't need to be the case here. You can treat the gluing constraints approximately, or you can treat them completely full theory. So that's really up to the model that you're investigating and how much resources you have to put into that investigation. All right. So let me take a step back from just telling you what an effective spin foam is and just give you the context again of a geometrical path integral. So the idea of a geometrical path integral is that you fix some property of a region of spacetime. For example, the geometry on the boundary of the region. And then we'd like to integrate over all possible geometries that fill in that boundary with some weight, just like a Feynman path integral. And so that weight would be e to the I, the action of that geometry. And this has just been the most, for me, the most inspiring context to get questions about quantum gravity. Questions come up again and again and again whenever you try to write down a geometrical path integral. So one of the questions that's very difficult is what's the right set of variables to use for these geometries? In particular, that choice of variable is tightly connected with the question of how do I take care of the symmetries, the diffeomorphism symmetries of the theory, and uniquely label my geometries. If I want to integrate over all geometries that interpolate a region, I need to know whether I'm doing that uniquely or if I'm overcounting and all these sorts of things. And finally, another one that I'll pick out, I'm picking out these three questions only because they're things that I'll talk about today. There are plenty of other questions you could ask as well, but is how do you compose regions? So if I have one region of space-time, how do I glue it to another region in order to get a consistent path integration over the combined region? So I don't know a compelling, sort of single principle that answers all these questions at once. It would be really exciting if we could come up with, a key insight that helped us to fix, the right set of variables, unique labeling of geometries, these sorts of things. But I'm going to take inspiration throughout today from the Feynman approach to path integration. And I just want to kind of give you the context for that. So on the left here, we have position as a function of time. And Feynman sort of had this beautiful picture of splitting up a portion of space by many, many slits. And you could imagine piecewise trajectories that went through those slits and connected to propagation points. In particular, what this does is give you a way to kind of think about a classical trajectory as a piecewise, completely linear description. So we're going to do the same thing with space-time, and this idea was introduced by Tullio Reggi, and it's easiest maybe to first think just of a two-dimensional surface. So a continuous two-dimensional surface would just be a curved surface. We're going to break it up into flat pieces, which we'll use triangles to describe. And if I glued, all six, maybe even seven in my picture triangles around, I would just get a flat surface. But if I take one of the triangles out and glue along the edges of the one that I removed, I can get a curved surface or an approximation, a piecewise linear approximation of a curved surface. There's two types of curvature here, of course. The pictures, it's really helpful to think about extrinsic curvature, where the triangles bend one next to the other, but you also want to think about the intrinsic curvature that an ant living on the surface would measure. And the reason I put the purple dot at the top here is that that's where the intrinsic curvature is concentrated in this picture. So it's sort of a distributional curvature, curvature that's concentrated on lower dimensional pieces of your triangulation. So I think most of you have messed around with one-dimensional quantum mechanical path integrals, and you know that there are several interesting features in these path integrals. So if I have an action that is of the form kinetic minus potential energy, and I discretize that action, then one of the most striking features to me of the path integral is that the additive structure of the action breaks up into a multiplicative structure in the path integral. Indeed, if it weren't for the fact that the terms in this sum are coupled through the intermediate point xk, then this would completely factorize, and you could get amplitudes for each piece, and you just get a product of those amplitudes. So this summative factorization turns into a multiplicative factorization in the path integral, and that's one of the structures we're going to be discussing and thinking about a lot today. In particular, I wanted to notice something about this, which is that if I take 2 points, let's say x1 and x2 in the picture here, and I insert an intermediate point, I'm going to call it Q just to make it easy to distinguish from the other points. I can take the term that has these 2 points coupled, and I can decouple them via Q. So I can further enhance the multiplicative factorization in the path integral by introducing this Q. Of course, it's at the cost of having another integral I have to do, but it's interesting that I can break it up. And there are several features here that I want to kind of emphasize because they're going to show up for us. If you allow Q to be another one of your discretization points, of course, there can be further dynamics at that point. You could evaluate the potential at that point as well, and you could introduce another kink, right? So if I had a very curved classical trajectory, inserting another point allows me to do a better approximation of that trajectory. On the other hand, if my trajectory is straight at that point, inserting Q did nothing to my trajectory, and my discretization doesn't really give me any new information. It turns out this is closely related to diffeomorphism invariance in the theory. When you have sort of straight line trajectories, you can see that adding more points doesn't actually change the accuracy of your path integral. This shows up in a very nice summary paper of Carlo's called The Magic of Dit Invariance, which was building on Bianca's work on reparametrization invariant theories. So we already can see this sort of thing at the simple trajectory level. And the last thing that I want to point out is that we can make very interesting constraints on our theory by how we glue at Q. So these gluing constraints are going to tell us a lot about the path integral, and that's actually what we're going to emphasize a lot in the gravitational case. All right, so with that overview, I'm trying to just give you all the preview of what I'm going to do for you. So today I want to show you a set of area variables for doing geometrical path integrals. Those area variables have a strange feature, which is that their classical equations of motion give zero curvature. So at first you would say, why do you want to use area variables at all? You're going to get flat space-time always. It seems like a really bad choice. But you'll see that for quantization, area variables are very, very nice. So the idea is to use these area variables, but add constraints in how we glue the pieces. And those constraints are what's going to give us non-trivial dynamics. So that's why I've been emphasizing gluing. On the other hand, those constraints are quantum mechanical in nature, and they don't commute with each other. So if you try to impose those constraints strongly, you would ruin uncertainty relations in the quantum mechanical theory. So instead of saying you have to constrain the theory this way, we're going to impose it weakly. We're going to allow fluctuations around the constrained configuration. And those fluctuations are key to getting the right dynamics. So I want to try and show you how that all fits together in some detail. This is the introductory part where I'm really trying to introduce you to the model. And in part 2, Seth is going to give you an overview of all of our results from within the model. All right, so I told you there's this Reggie calculus. Let me say a few more words about why it's important to use Reggie calculus. If you think of a continuum region, you would have infinitely many points. And so your metric has a value at every single one of those points, and you have an infinite number of degrees of freedom. For doing numerical computations, that's just going to be impossible. So one of the advantages of working with Reggie Calculus is you're going to cut down your degrees of freedom to a finite number of pieces, right? We have a flat triangle, we're gluing to another flat triangle, and all we have is how they're glued together. And so it's a finite number of degrees of freedom. So this is essential for doing numerics. It also is going to be really helpful for sort of taming the theory. So that's one reason to think about Reggie calculus. Let's build up in dimensions so you can get a clearer picture for how it works in 4 space-time dimensions. So I already explained the picture here, and we saw that the intrinsic curvature is concentrated at what Reggie called bones. In this case, it's a d minus 2-dimensional point in 2D. But let's go one dimension up and think about 3D spacetimes. You could imagine taking an orange and cutting the orange up into slices, wedges, and you could remove one of those wedges, and by gluing the 2 oranges that are left naked, you get a curvature, and that curvature is now concentrated along an edge instead of a vertex, instead of a point. So that gives us, in 3D, the bones are 1-dimensional edges, and the curvature is measured around those edges. So if the ant walked now around this edge, it would measure intrinsic curvature around that edge. In 3D, there's a beautiful kind of coincidence, which is that the variable that describes the length of the edge, which is a natural variable for describing the metric of the geometry, and the angle that measures the curvature around the edge are just automatically symplectic conjugates of each other. They automatically provide you a nice phase space that you can work with and study directly. So 3D quantum gravity is very, very nice. And we know this from many different directions, but in particular, it's very nice in the path integral. And the first approach to 3D quantum gravity, the Panzano-Reggi model, Maite introduced you to. So that's partly why we use it, is it's got this beautiful conjugacy of the natural variables in the theory. Unfortunately, in 4D, that's not the case. So in 4D, we work with 4 simplices. These are just the generalization of tetrahedra. So it's 5 points in a 4-dimensional space that you connect to each point by an edge, and it builds a generalization of a tetrahedron. Then you can glue those tetrahedra together through, glue those 4 simplices together through tetrahedra. In particular, 2 tetrahedra are going to meet along a triangle, and the bone, the object that carries curvature in the 4D theory, are these triangles. And again, you can have the ant walk around that triangle, and in traversing that triangle, it gets a measure of the curvature inside, and that would be the conjugate variable to that area, the area of the triangle. So here we have to make a choice. We're forced to make a choice. We either have to work with the edge lengths of the 4 simplex, which are the natural metrical variables that are familiar to all of you, I suspect. But the conjugate variable to these edge lengths is a very complicated combination of factors. Or we can work with areas, the areas of triangles in the simplex, and the natural conjugated area variable is the curvature around that triangle. So this gives us a nice thing, but now we have to think about metrics or geometries in terms of areas instead of in terms of lengths. So that's the trade-off we have to make. So in loop quantum gravity, there's been a number of years of investigation of this line of thinking, and the upshot has been that the area variables are very nice. They quantize nicely. They give you nice discrete spectra, and so we're gonna be taking the perspective that you should work with the area variables and their nicely conjugated curvature angle. Okay. So that's an overview of Reggie calculus and what the choice of variables we're going to make. But this is an
Can I ask a question?
Please go ahead.
So in 3D, I have a sense in which there is an angle as you go around the length. But in 4D, the area is like the configuration variable, and the angle is a dihedral angle. Then it's a solid angle, right?
Yeah, so it is. It's a if you think about the normals between the two tetrahedra that you're gluing along, it's the four-dimensional that those two tetrahedra have four-dimensional normals, and it's
Mm-hmm.
the inner product of those four-dimensional normals that measures the curvature around that triangle.
Okay. All
Does
right.
that help?
I just have a hard time visualizing it.
Indeed, 4D is always difficult to visualize, right? We have to kind
Okay.
of make extrapolations, but the
Right.
definition is just like the definition you would use in 3D, except you're using tetrahedra and they're four.
Right. Oh, thanks.
Yep. Another way to think about it is the Riemann tensor takes, it has four indices. Two of those indices are a bivector that tells you what plane you're measuring curvature in, and the other two are moving around that bivector. So that's another way of thinking about what's going on. All right, but I want to try and keep the geometry more relaxed to start out. Let's start out in lower dimensions and think about lower dimensions. Most of us have never thought about area descriptions of geometry. What can we do with this? Well, there's a classical result that you may have never seen, but it's a pity because it's a beautiful result. It's due to Heron, Heron of Greek origins. And it gives the area of a triangle in terms of the edge lengths of the three edges of the triangle. It's this beautiful symmetrical result. You can even memorize this result. It's so easy. You just add up the lengths, and then you put a minus sign on each one of them separately, and that gives you this product that is the Heron formula. So I can work back and forth between the edge lengths of a triangle and its area. It's not so bad. But there's a second result, and this result is due to Hermann Minkowski of special relativity fame. So Minkowski showed that you can actually find the geometry of a tetrahedron from the so-called area vectors of that tetrahedron. So what is an area vector? It's a three-dimensional vector that is perpendicular to the face of a tetrahedron. Let's focus, say, on face one. So it's got the direction is normal to that face, and its magnitude is equal to the area of that face. So what Minkowski proved is that there's a one-to-one correspondence between the geometry of the tetrahedron and the closure relation that its area vectors add up to 0. So this is a beautiful classical result. I have lots of comments about how you prove this result, but I don't want to go through them right now. But if you have questions about it, you can ask me. But let's just take it as granted for the moment that you can get the geometry of a tetrahedron from its area vectors, and the area vectors have to satisfy this closure condition that they add up to 0. Why is this so interesting? Well, this is where loop quantum gravity really comes into the picture strongly. There's a profound change in perspective. I was describing those area vectors as just vectors in R3. But many of you will know that the Lie algebra of the rotation group, SO3, is isomorphic to R3. You can go back and forth, no problem. And so let's reinterpret those area vectors not just as having magnitudes equal to the area and directions normal to the face, but as generators of the Lie algebra. Well, why is that significant? Well, that means this closure relation that we just talked about, the generators, when you add them up, they generate overall rotations of the tetrahedron. We know that overall rotations don't change the geometry. And so the significance of the closure relation that these area vectors add up to 0 is the fact that the geometry isn't changing when you rotate the tetrahedron. So there's this correspondence in thinking between the SO3 group and the geometry of this tetrahedron. In particular, this is a discrete version of the Gauss law that Maite introduced you to, invariance under rotations. It's a beautiful result. Who thought of this? This is a crazy idea. It's a beautiful idea. I mean, one intuition I can offer you, which I learned from Wolfgang Wieland, I like it a lot. You know from planetary orbits that angular momentum, SO3 generators, are related to equal areas and equal times. So there's kind of a beautiful relationship between area and angular momentum. That's what we're seeing here. All right. So we're starting to see that we can build geometry out of areas. We can do more than that, and this is going to start to connect with Seth's discussion of Lorentzian geometries. It turns out that you don't just have to think of these A's as SO3 generators, you can also think of them as SO21 generators. In either case, whether it's rotations or boosts, the closure condition expresses invariance under the geometry of the tetrahedron under that symmetry. So this is a beautiful, beautiful result. All right, let's do a little counting. The counting is going to show that we have a problem. You all know how to describe the parameters of a tetrahedron. You can just think of the parameters as the edge lengths themselves. And we can count those. There's 6 of them, right? 3 on the triangular base and 3 going up to the peak. So there's 6 parameters that you need to describe the geometry of a tetrahedron. Well, we have 4 area vectors. Each one of those area vectors has 3 components. So there are 12 components of the area vectors. That's clearly overkill, right? What happened? Well, we know that there's some things that are invariant under rotation, the magnitudes of the areas of the faces. So maybe we should just work with those. But there are only 4 magnitudes of the area of the faces. So we have an we can't make the number of parameters we need if we just work with those 3 rotational invariants. So the trick is to use closure. And if you use closure properly, you can actually pick out exactly the right number of parameters. So let me introduce a set of variables. This set of variables is just the dot products of any 2 of the area vectors. So if you take a dot product of the area vector associated to triangle T, and that with triangle T again, you just get the magnitude of the area, and it'd be the magnitudes we already talked about. If you take the dot product of triangle T and triangle T prime, you're going to get the dihedral angle, now the 3-dimensional dihedral angle, and we have a rotational invariant to describe the geometry of the tetrahedron. So these, we'll call them P variables for the rest of today. These P variables are very nice. What is this sign factor out front? SGN just means the sign, like plus or minus, of the volume squared of the tetrahedron. Why am I putting that there? It's to cover both the Euclidean and the Lorentzian cases. If you put that sign factor out front, these variables are nice no matter which kind of geometry you're working with. In other words, you could think of it as being more like Euclidean geometry or more like hyperbolic Lorentzian geometry. Okay, so how many dot product variables do we have, and how do we see that they give the right number of variables for the problem? Let's do this counting again and think about it carefully. We know there are 4 triangles in the tetrahedron. So that means there's, a priori, you could arrange a 4x4 matrix and it would have 16 entries. But of course, the dot products are symmetric, right? So the entry PT1, T2 has got to be the same as PT2, T1, right? So we can take out the entries above the diagonal or below the diagonal, whichever you like. That's 6 of them. So we go from 16 down to 10. And then the dot products of the A's with the closure relation give us 4 equations that relate the P's. And so we can take out those relations and we land on exactly 6 independent variables. And these are the rotationally invariant, in this Euclidean case, rotationally invariant variables that perfectly describe the tetrahedron in terms of its area variables. So we already know how to think about these. 4 of them are the face areas, and the other 2 are these dot products. It turns out the dot products that are independent have to come from edges that are not opposite from one another. That's not obvious. That comes from these 4 equations. You have to study these equations a little carefully, and you'll learn that if I tried to use 2 edges that were opposite, I wouldn't actually span all the variables. I have to use 2 edges that are meeting at some vertex. What am I describing? I'm kind of giving you a way of thinking about things. The reason I'm using this formalism is because it works for all the different kinds of geometry. It's very general, but I'm really just describing 3D dihedral angles. So to describe a tetrahedron, you can use 4 areas and 2 dihedral angles. It's just that you have to be careful what to use, either cosh or cos, depending on the geometry. And I'm just going to move the cosh and cos to the other side and work with the p's. It's easier. So try it, see if you agree, but I think you will find it's easier to work with the cosine or cosh of the dihedral angle. All right, that was all classical geometry described in terms of area variables. So we'd like to study a quantum theory of gravity, and so we should bring in quantum mechanics. And we can start by just quantizing these area variables. This is the second place where thinking of these as SO3 generators is profound. SO3 generators are angular momenta, and so we can think of just quantizing exactly like you've done in any quantum mechanics course you've ever taken, quantize angular momenta. In particular, we'll think of the area variables as operators that are just proportional to angular momentum operators. This proportionality factor is going to turn out to be significant because think about what j squared, the operator j squared, represents in this case. It represents a squared. So the spectrum of areas is just square root of j times j plus 1, like you know from quantum mechanics. And what this proportionality factor is doing, we call it the area gap, is controlling the spacing between the levels of the area spectrum. In particular, to get units right, my j is dimensionless, so I'll put in the Planck length as my units. So Planck length, I'm using the same 8 pi g variables Carla was using this morning. Planck length is given by this formula. If I work in the regime where the spin that labels the spectral levels of area, where that spin is large, then I can approximate this square root as just square root of j squared, which is just j. So my spectrum looks roughly equally spaced in the large j regime, and the spacing is determined by this area gap parameter, which is also known as the Barbera-Mirzi parameter, and by the Planck area. That's the quantization. We've suddenly managed to find a quantum geometry of these tetrahedra just by working with area variables. It's quite beautiful if you ask me. Again, all of this generalizes to the Lorentzian case. I'm concerned about time, so I'm going to skip over this, but the slides will be posted for you and you can think about them. The key is to switch from thinking about SO3 or SU2, its double cover, to thinking about SO21 or SU11, its double cover, and you can think about generators in that context. The most intriguing part of this quantization of the geometry of a tetrahedron is that the variables don't commute. So remember, our variables were the 4 areas and their 2 inner products at edges that were adjacent. And we can just start to write down, we know angular momentum, we know it either as Poisson brackets as a classical phase space or as a quantum commutator, either way. I'm going to write it classically here. The Poisson bracket of one of these angular momentum generator components with another one of the components is just the structure constants with a proportionality factor that I put in. And you can work that out in both the Euclidean case or the Lorentzian case. This is just the familiar Jx with Jy is Jz commutation relation. And we can use that commutation relation to calculate what's the commutator between these 2 angle inner products that we were studying. So you put in the 2 p's, you figure out, oh, well, they only share triangle T prime. So that's the one that's going to have a non-trivial bracket. That bracket is the epsilon symbol. I put in all the factors and I find a triple product of 3 areas. So here's my first exercise for all of you as students. It's a wonderful exercise. I just think it's beautiful. Start out with the volume of a tetrahedron that you know well. Take its 3 area vectors and form their triple product. Find how the area vectors are related to edge length vectors and prove that the triple product of area vectors is just the volume squared. So it's an elementary calculation, but it's beautiful to see that this commutator is directly related to the volume of the tetrahedron. Okay, so this is very significant. There's kind of 3 big takeaways I want you to have from it. For fixed areas, these degrees of freedom do not commute. So that's the main thing. If we want to think about this as a quantum mechanical problem, we can't think of this tetrahedron as having a definite geometry. This tetrahedron is a fuzzy geometry. It has some uncertainty relations on its parameters. So you have to think of it as a blurred tetrahedron at the quantum level. The parameterization we've given is famous in the literature. It's called the Kapovich-Milson phase space and has been studied extensively. So no matter what, one shape parameter is going to have to be uncertain, or we're not describing a consistent quantum geometry. Okay. So we overviewed Reggie Calculus. We went deeper into that geometry in terms of area variables and have understood the quantum geometry of tetrahedra. So what if we want to do Reggie Calculus with this area variables? The key here for us is that by working in area variables, we're going to be able to bring in the quantum ingredients of the theory more directly. So we're going to work with triangle areas. So again, just to say it in words, we're going to work with 4 simplices. What are 4 simplices? There's just 5 vertices in your space. Those 5 vertices, we connect every pair of them. That gives you 10 edges in the 4 simplex. It actually also gives you 10 triangles. If you look at it carefully, this is just 5 choose 2 and 5 choose 3, if you want to think that way, and 5 tetrahedra. And so how do we think about the area and length descriptions? How are they related to each other? The key is to think about the functions that gave the areas in terms of the lengths, this Heron formula. I put it at the bottom of the slide for you again. So using the Heron formula, I can go from any length description of my 4 simplex to its areas. But what we really want is to be able to describe the geometry in terms of the area. So we want to invert this function. Notice my notation here. When I'm talking about functions, I use capital letters. When I'm talking about variables, I use lowercase letters. So I want to invert this function A as a function of L to find the lengths as functions of the areas. That inversion involves all the triangles in the simplex and all the edge lengths in the simplex. But luckily for us, there are exactly 10 edges and 10 triangles. So in a 4 simplex, this makes sense. Still, you might worry, this is going to be a system of algebraic equations, and systems of algebraic equations tend to have a whole set of roots, right? So I'm going to get a whole set of areas that correspond to some given set of lengths, or vice versa. So what do I do? Well, the key is these variables we introduce, these inner product variables, they distinguish the roots. Turns out you can show that they're enough to tell you which root you're talking about. So now I have a dictionary that allows me to get from lengths to areas or areas to lengths, whichever I like. That dictionary is important because Reggie initially wrote down Reggie calculus in terms of length variables. So let's write down what is the Reggie action. The Reggie action in 4D is really simple. It's just a measure of the extent of a region over which there's curvature times the curvature of that region. What's the curvature? It's exactly that idea, the picture that we saw. You take the triangles, you remove one, and you ask, what's the difference in angle around those triangles from 2 pi? 2 pi would be flat. I got all the angles to give a flat thing. If I subtract something less than 2 pi, then there's curvature at that point. So this is our Reggie action, but Reggie was thinking of these areas as functions of the lengths and of the dihedral angles as functions of the length. Just to be clear here, the thetas are the 4D dihedral angles that were being asked about earlier in the talk. Nonetheless, you can take this action, you can do a variation with respect to lengths. That variation gives you these equations of motion, and beautifully you can try to do numerical computations and check that for finer and finer triangulations, this does indeed limit to the Einstein equations. So you can recover non-trivial curved geometries from this Reggie calculus described in terms of lengths. What about areas? We've seen that we can find functions L that give us the lengths in terms of areas. If I start from my Reggie calculus, well, now I'm going to take areas to be variables. That's how they became lowercase. I can also take my epsilon, my curvature. I can take it expressed as a function of lengths, replace the lengths by my functions, and I get the epsilon as a function of areas. So now I have my so-called area Reggie calculus action. There's something fascinating about this action, which I previewed for you at the very beginning, which is if I now vary the area variables, There's a famous identity from mathematics called the Schlafly identity that says that the sum of areas times the variation in dihedral in curvature angle is exactly 0. This is the Schlafly identity. So the variation of my action tells me that the curvature, the term that came just from varying the a's, is 0. So my equation of motion is that my space-time is flat. That's very unfortunate if you want to try and use this to study gravity. So this is the difficulty of using area variables, at least initially. And it shows that we can't work with these areas completely unconstrained. All right, so we should introduce constraints. In fact, this shouldn't have been a surprise to us. When we think about gluing two four simplices together, we're going to glue them through a tetrahedron. That tetrahedron I've tried to highlight here with the 4 orange dots. I've done it on both of the four simplices, and you can imagine gluing those two four simplices through those 4 orange dots. There's just a differing number of degrees of freedom here. If I glue all the edge lengths in those two tetrahedra, then there's 6 edges that get matched. But if I glue the areas, there are only 4 areas that get matched, and clearly there's more freedom left over. So there's a mismatch that we have to resolve. And all this analysis that we just did of tetrahedra and their inner product variables is exactly what we need. We need to impose that the inner product variable for our tetrahedron, tau, in the simplex sigma, is given by the one that you would expect from the length variables. We've expressed those length variables in terms of areas to give this constraint in terms of the areas. So when we glue these two tetrahedra from these two four simplices, then the constraint that we'll impose is that when you calculate those inner product variables from the sigma simplex and from the sigma prime simplex, they exactly agree. Now I've really glued the two tetrahedra, and now I should have the right number of degrees of freedom to match the geometry. Okay, this is great. We found a way to glue simplices to build bigger and bigger triangulations, but there's an ugly aspect of this. The ugly aspect is that these constraints depend non-locally. That is, they depend on the area variables throughout the entire simplex, beyond the tetrahedron that we glued. So that's going to start to spread out. How you're gluing depends on variables throughout the entire triangulation and be very difficult to follow. So what we want to try and do is localize these constraints. So instead of working in area Reggie calculus just with the area variables, we're going to return to thinking about this 1D path integral and see what did we understand there. We understood that the coupling was through the gluing, right? The coupling of the different parts of the integration was through the gluing point. So can we deal with that gluing point? So we just add more variables to our theory. It's just like adding in the q's. And just as I've been doing throughout, we'll call lowercase variables the p's. We're going to add these additional variables in. And the requirements, the constraints that we'll make is that the p variable has to be equal to the p constraint that comes from the areas of that simplex. This has localized it so that the constraint just depends on the local variables in the simplex right there. The one caveat with this is that we've seen that these p variables don't commute classically. So if we want to impose these constraints on the quantum theory, we have to deal with non-commuting constraints. And non-commuting constraints, you may or may not know this jargon, it doesn't really matter. They're called second class. The reason people make a big deal of calling them by a name, second class, is that we know we can't impose these constraints strongly. If we impose them strongly, we destroy any uncertainty relation between these two variables. So we're forced to use these constraints as weak constraints. All right, so I'm just trying to build up all of the results that we've got so far. Here's our area Reggie action again with the curvature angle. I'm just expressing it in terms of area variables and dihedral angles. And when you express it this way, you see that it breaks up into a sum over triangles and a sum over simplices. In fact, we can even include boundaries just by keeping track of whether the triangle's on the boundary or not. And in this way, you find a really nice structure for your total action. It's a sum over all the triangles in the triangulation, a sum over all the simplices in the triangulation, and finally, we add in these constraints, and the constraints impose that the gluing is good whenever we glue two tetrahedra. It's a completely additive action, and that's going to be really nice in the quantum theory where we're going to get a completely product form for our path integral. We want to bring in a quantum ingredient. The quantum ingredient that we bring in is the area spectrum. That area spectrum we derived, it's proportional to the area gap times the Planck length times the spin. But bringing in this last ingredient, this quantum ingredient, that I'm only going to allow my area variables to have certain values, that imposes yet again a tension. The tension, I'll use this as an illustration for it. You know the Greek mythology of Scylla and Charybdis, the sea monster and the great whirlpool, and you have to navigate between these. So if we impose the constraints too strongly, there's going to be no tetrahedra with the right areas, with these half integer areas that satisfy those constraints. You just geometrically can't do it. So we can't impose them too strongly. If we impose them too strongly, we reduce the density of states, would be a technical way to say it. We reduce all the states there are. On the other hand, Milo, I can't right now. On the other hand, imposing dynamics imposing them too strongly imposes dynamics that don't match general relativity. So this is the upshot that we have to go to these imposition constraints. Weak imposition of constraints, excuse me. So here at last is our effective spin foam model. And I've written it in as close a way to how Maite wrote it as I could. The partition function is a sum over the spin labels of your triangulation times a measure factor times the exponential of this sum factorized Regi total action that we just saw. Because it was sum factorized, it breaks into a product factorization, amplitudes associated with triangles, amplitudes associated with simplices, and gluing constraints. The amplitudes for the triangles and simplices I've listed here. I'm just plugging in the formulas that we had above. And the real thing that we need to study in the effective spin foam is what are these gluing constraints? How do we think about these?
There
So
are 10 more minutes left to the end of the first hour. So if you want to have some question break at some point, just.
Thanks so much, Johannes. I will wrap up this part soon. As we were just discussing, if we implement these too strongly, that is, if we say the G's are equal to 1 if the constraints are satisfied and 0 otherwise, we completely kill our path integral. There's just no states that satisfy it because of the discrete area spectrum. And that's the key fact that leads to our weak imposition of the constraints. Luckily, there's a beautiful technology for this in loop quantum gravity. So Maite described very briefly the intertwiner space of loop quantum gravity, and you can build coherent states of a geometry that are peaked on a particular geometry, peaked with their intertwiner having exactly the face areas and the angles that you want. And so we can glue our two tetrahedra peaked on the geometries that we want in each of the simplices. So this is going to be the way we'll try and build in the gluing constraints of the path integral. So this is a summary of it. The things that we've done in numerics, and Seth will present many of these, is consider simplified triangulations where many of the areas are equal and the geometry is a little simpler. This allows you to calculate more robustly. We've approximated the coherent inner products by Gaussians. This is the first place where an approximation comes into the theory. We've used a Gaussian just because we expect the inner product to be Gaussian. And we know what we think the width of that Gaussian should be. It should be proportional to this non-commutator. So this is the physical input that we use to determine the weakness of our constraint. And we consider how this path integral scales with the spins, the areas, and with the area gap. So let me just give you an overview of all of these results and summarize for you. In quantizing the geometry of 3D and 4D triangulations, we use these area vectors as angular momentum operators. We scale by this area gap. We leverage closure and global rotations to parameterize the full geometry of the tetrahedron. And then gluing tetrahedra to form a 4-simplex and gluing 4 simplices, we have to impose constraints to ensure a consistent length assignment. And there are 2 non-commuting constraints per tetrahedron. And this is where a lot of the physics and the theory comes in. Uncertainty relations prevent us from a sharp imposition of the constraints in the quantum theory, and so we have to implement them weakly. A different approach than that would be to impose the constraints at the classical level and then quantize the reduced phase space. This has been thought about a lot in the community. The trouble is that it leads to a very difficult phase space with a complicated topology. So this is something that I hope one of you might be interested in. I'm summarizing the model one more time. I wrote it in a very detailed form for you so that you could really think about how would I compute this thing. But let me back out from that detailed form and just give you conceptually what's going on in the path integral. The pieces are 4 basically. There's a measure factor. There's a standard action weight like you would think of. But the action weight for this theory is the area Reggie calculus action. There are constraints that I did not get to discuss. These are constraints on the fact that we're using triangles. So you know triangles satisfy triangle inequalities. Turns out tetrahedra and 4 simplices satisfy generalizations of those inequalities. And we have to make sure not to construct a nonsense tetrahedron or a nonsense 4 simplex. So you just take into account all the generalized triangle inequalities, and that's going to actually make your theory easier to compute because you have to compute over fewer configurations. This is another advantage in the numerics. And finally, the most important conceptual ingredient is that we introduce constraints that glue simplices together. That's where the non-trivial dynamics is going to come from. I really want to leave some time for questions, so I'll stop there. Seth will take up results that come out of this model. But there's another beautiful topic that I just want to flash for you so you get to think about it. Weak constraints, I don't think we have enough intuition as a physics community about weak constraints. These are constraints that are imposed, not strongly as an equation, but as a Gaussian. It turns out when you have theories with weak constraints, there's an interplay between the different parameters of the model. And your semi-classical regime is not just a small h-bar regime. You have to think about it in a richer way. So the semi-classical regime in this case of an effective spin foam ends up being a really interesting interplay between the small h-bar limit, which is a large J limit, a large area limit, and the area gap parameter gamma, and the curvature at the triangle that you're studying. These 3 parameters have to all be related to each other, and it's only in that regime that you really expect a semi-classical behavior. So I just want to preview that because Seth is going to talk about it a little bit more. With that, I'll leave up my summary here briefly. We can talk about it more if you have questions about it. I want to thank you, and I imagine we'll have 5 minutes for questions now, but you may have more. Here's my contact information. I'm happy to field any questions we don't get to today. Mushin, I think you had a hand up first. You want to ask?
Thank you for the first part of the talk. Yeah, so I asked to unmute Mushin.
Oops.
Mushin, if you're having audio trouble, you could put it in the chat too. Maybe should we take Deepak's question before?
Yes.
Hi, Hal. Very nice talk.
Thank you.
So I have a question about your action. So is your action purely imaginary or complex?
It's
because
complex.
we know it's complex.
It's complex in general. When you deal with the Euclidean theory, it's pure imaginary. But when you deal with the Lorentzian theory, the dihedral angles that go into the curvature angle, those are actually complex dihedral angles. It has to do with Seth will go through this in some detail. At any rate, in general, it's a complex action depending on the space-time geometry.
I see. Okay. And then second question is, are you expecting this effective model in some sense sometimes will converge to the EPRL or some other spinfold model in certain limit?
Yes, absolutely. So right now we're taking this very simplistic approach, right, of gluing simplices via Gaussians, right? I think it's a good place to start because it makes our numerics extremely efficient, right? And we've already been able to reproduce results of length Reggie calculus from this area Reggie calculus perspective. But presumably you can find the exact constraint function. It's probably not exactly a Gaussian, but you can find the exact constraint function of EPRL, and then for that function you should recover EPRL exactly.
Oh well, but I mean the full. How about the full amplitude? So the constraint, yes, it's very similar to EPRL, but the full amplitude, whether you can go back to EPRL, or I mean go back and forth, or EPRL certain. Well, anyway, so certain relation with the EPRL model from the vertex amplitude or full amplitude point of view.
That is what I'm addressing. I'm saying if you use the right capital G functions, you'll recover the full amplitude of EPRL.
Okay. So I see. Okay. Thank you.
Great.
Okay, then there's another question.
Right. Hi. So beautiful talk, Hal.
Thank you.
I have two questions. One is how do you get SU11? Like, is that in the context of the 3D case or the 4D case? Like, that's not clear to me. And the second question, yeah.
Please go ahead.
And second question is about the emergency parameter. Like, I mean, one might think that the emergency parameter should also have some renormalization flow. And so as you glue more and more of these simplices together, right, you are effectively performing that renormalization flow, right? You're going to larger and larger volumes. So, but in this picture, there doesn't seem to be any sort of possibility to see a renormalization for the emergency parameter.
I agree with you. So sorry, let me take them in order. So first you asked about SU11. So I raised SU11 in the context of the 3D geometry of a tetrahedron. Of course, we're thinking of these tetrahedra as being embedded in a 4-dimensional space-time, but let's just think about the geometry of that 3-dimensional tetrahedron. If that tetrahedron has some faces that are time-like as well as faces that are space-like, then you can't just work with the SO3 or SU2. You have to deal with the fact that there's a time-like component in your tetrahedron. And in particular, you should have boost symmetries of your tetrahedron as well as rotational symmetries. And so that's the context in which SU11 comes up. You can just think of it as SO21 if that's easier to think about. It's just
okay. So it's just for the Lorentzian. Okay, fine. Yeah.
That's right. Regarding gamma, I completely agree that it should be renormalized and that it'll be interesting to study its renormalization. Bianca has already begun work, so her very most recent paper on the archive looks at lattices and looks at renormalization of exactly this effective spin foam in a lattice context. So she's begun that work, but I don't think, and maybe Seth can comment on this, I don't think we have specific results regarding renormalization of gamma yet.
Yeah, not yet. It's still.
I mean, like, can you think of some physical mechanism, some idea of how it might happen? Like, not, I mean, results always take time. But...
Well,
If,
I
if
mean,
the,
as you pointed out, what you're doing when you renormalize here is you're kind of, it is very much a geometrical coarse graining, right? So you have a triangulation that you've broken up into pieces, and you're working with a certain area spectral gap for that triangulation. Now I'm going to coarse grain that triangulation and think about it at a different scale. And it's no surprise that I don't think that the area spectrum might shift when I change to that different scale. That is, that the gaps between levels might be described in a different way.
okay, thanks.
Yeah.
Okay, there are no more raised hands or questions in the chat, so I think we can continue with the second part.
Wonderful. Thank you, everyone, again.
Yeah, thank you too.
Okay, let's see. Okay, can you see my screen?
Yes.
Okay, thank you. Yeah, thank you so much, Hal, for this nice talk and making my job easy. And thank you everyone for also showing up to this talk. I will present the second part of the effective spin forms. And as Hal mentioned in the beginning of his talk, this is based on these 3 papers. So if you have time, you can always have a look at these 3 papers. It's nicely describing all these. There's a short version in this PRL if you're interested. Okay. And so before I begin, I want to say thank you to the organizers for organizing this school. I have learned a lot. There's a lot of nice lectures given by many great professors, so I'm very grateful. And also thank you for inviting me to also present at these lectures. Maybe I count myself as one of the junior people, so I'm very happy that you also allow junior people to present. And so, and I also want to thank Hal, Bianca, Jose, who are my collaborators for this interesting work. Okay, so so as an outline for this lectures I'm going to give, it will be maybe an intersection of some lectures and also overview of results. I mean, to present numerical results as lectures, we have to go through like some codes, but that's gonna take a long time. So I just decided to present an overview of some results. And yeah, you see here, we will tackle Reggie Calculus again. We've seen this throughout, but I think it will be good. We go through again. And here I'll focus more on the Lorentzian aspects of this Reggie Calculus. Okay. So yeah, let's begin. So Hal made a very nice talk and summarized the many reasons why area variables are so nice to use when describing geometries in 4 dimensions. And so actually there are many other motivations you can also say about why area variables are nice. In LQG, I mean, obviously we use area variables even in spin forms. There are these, if you start from the BF fraction, these B fields are associated to surfaces and areas. Also, if you think about the black hole entropy formula, it's related to the area. And so there are many motivations why you would want to use these area variables as your fundamental variables in describing quantum geometry. And one of the key results we saw was that these area variables, they have discrete eigenvalues. And maybe not to repeat so much, I can give you like maybe an overview of how you can expect these discrete spectra. So maybe from LQG. So as we know, the area variables in LQG are usually conjugated to the Ashtika connection, but Ashtika connection variables, which you can express as the spin connection plus the extrinsic curvature proportional with a proportional constant known as the Barbero-Imesi parameter. And these are exponentiated, right? And so this is the reason why the conjugated variables, which are areas, have come in discrete spectra. But if you think of time-like areas, usually if you have time-like areas, the conjugated variables are described by Euclidean angles, curvature angles, and these are already compact. And so you have that the area variables for the time-like ones are also discrete. So this is just like a brief, maybe a naive analogy of how you can think of area variables as discrete. And we also saw that, okay, we don't just focus on these area variables. Those are not the only parameters appearing, but there are some 3D variables, I'll call them the P variables. And these, you can think of them as describing angle variables. And we saw that they have non-commuting algebra. Okay, and yep, so yeah, because of this non-commuting algebra, okay, maybe actually, so the point is that if you have these area variables and these angle variables, they are not totally free, like, but they depend, I mean, there are some constraints between these variables if you want to describe the full geometry. And the constraints in LQG are usually referred to as the simplicity constraints. And here you can think of them as these simplicity constraints they can fix your P variables, the variables, inner product variables or the angle variables as functions of your areas. And another property is that these constraints are second class nature. I'll mention this. And if you compute the Poisson brackets, you see that they are proportional to the gamma parameter. And so this serves as already an anomaly parameter in your quantum mechanics. Yeah. And so we will see that if you want to get back to a consistent length assignment, you have to impose these constraints. And then this is what we are going to do in effective spin forms. And also in the same spirit, this is what spin forms try to do. And so the point is that here we keep the dynamics and principles of loop quantum gravity, but we are going to use simple amplitudes. And Hal already described how we can get simple amplitude from Regi action, from discrete geometry and stuff like that. In spin forms, it also follows the same principle, but the amplitudes are much complicated. And that's why spin forms are very hard to tackle numerically or even analytically. Okay. And here I cited this paper here because there's a formulation where you can start from not just use some higher gauge group, and then it can lead to simpler amplitudes. It's also like a spin form type amplitude, but they are simpler than just using the BF type amplitudes. Okay, so yeah, so the point of effective spin forms is just to take these two things seriously, which are the discrete areas and the constraints seriously, but Hal described how the constraints are tricky. And so here we try to impose them weakly. I'll describe this in maybe some few details. Okay, so here I also show up Hal's conclusion slide. You saw this effective spin form partition function. And so there are the measure terms here, the area Regi action, and maybe to say a few words about this, the measure term. So this, you can think of them, maybe you can think of fixing these by demanding some coarse grain invariance under coarse graining, or some approximate diffeomorphism invariant or discrete invariant. And also, in addition, yeah, there are these generalized triangle inequalities. And since I was describing Lorentzian spacetime, we will have a feel of how all these terms appear in the spin forms and how you can leverage all these terms to build a proper quantum geometric path integral. And so the point is that from these spin forms, you can study so many features about quantum gravity. Like you can easily sum over orientations by allowing both plus and minus as orientations here. You can study color structures, and we will see how these all appear. Okay, and so yeah, Reggie Calculus again. It has appeared a lot throughout this lecture series. Maite mentioned it at Wilson when they were treating the GFT. Also, Valentin described a combinatorial version of Reggie Calculus, and Hal already mentioned Reggie Calculus. And so, yeah, I will not go in much detail, but it's just to say that it appears quite naturally in describing physics of LQG or spin forms. And it's a particular choice of piecewise linear approximation of some spacetime. So mathematically, this is it's a choice we make, but one can have other choices. You can, I don't know, choose maybe piecewise analytic functions, but this is not the direction we are going to go. And so here I show you how you can think of these simplices. I mean, in 2 dimensions, you have the building blocks are triangles. In 3 dimensions, you have the trahedra. 4 dimensions, 4 simplices, so on and so forth. And when Reggie introduced this description, he described the geometry of these simplices using edge lengths. Okay, but as already Hal mentioned, there are other formulations exist. Hal described the area version. But in most of the lecture series, we saw maybe the length version, or you can even set all lengths equal and describe a combinatoric version and so on and so forth. When Reggie actually introduced, he deemed this as a coordinate-free description of GR. Okay. And okay, maybe not to repeat so much here. Also, so the point is that you can describe curvature from these Reggie geometries by concentrating on the 2 dimensions lower simplices. So if you're in 2 dimensions, the curvature is concentrated at points or vertices, and so on and so forth. So here I put here not 2 pi, but float value for the definition of a deficit angle or dihedral angle, which describes the curvature, because I want to generalize this to both Euclidean and Lorentzian signatures, and we will see how this appear in the Lorentzian signatures. And maybe here, I can give an intuition of how to think about angles in higher dimensions. Maybe one way is to, it's usually very difficult to imagine this in higher dimensions. So for example, in 4 dimensions where areas are concentrated around triangles, it's hard to imagine the curvature, but you can think of it by projecting. You can always project a simplest to lower dimensions, or part of a subsimplest to lower dimensions. And so for example, in 4D, you can project, say, the triangle to a point, and then the curvature around the triangles can be described in the 2 dimensions where you can picture these. And so if you play this game, you can always try and imagine how curvature works in higher dimensions by using projections. Okay. So here, to give you an intuition about how curvature works in Lorentzian spacetimes, I have this slide to explain to you a little bit of how you can think about this. And this is already described by Raphael Sokin in his recent paper in 2019. And the point is that if you think of Euclidean angles, we have a nice intuition about Euclidean angles. You can think of it as parameterized by points on a circle if you're in 2 dimensions, right? And in the same way, in 2 dimensions, you can think of Lorentzian angles as parameterized by points on a hyperbole in Minkowski spacetime. But in Minkowski spacetime, we have the two light cones, these 2 light cones here, split the Minkowski spacetime into 4 disconnected regions. And so the regions are not continuous. And so describing curvature around the point it's non-trivial, basically. And so the way Sokin described this is using wedges. So he called them wedges, which you can just think of them as just vectors, but you specify the regions between the edges. So for example, if I talk of the angle between these 2 edges here, I should specify which region I'm talking about. So for example, the angle between these 2 edges in this region is not the same as the angle in this region. Okay. And also how we will build these angles is we will use one property which is already present in the Euclidean, which is the angles add up. So if I have an angle between region A, region B, and I combine these 2 regions, then in Euclidean, the angle A plus B is just the total angle for these 2 regions. And in Lorentzians too, we want to keep this additivity principle, that the angles between these 2 regions are the sum is equal to the sum of the angles between individual regions. So if you require this, you can actually specify angles in Lorentzian spacetime. And also, actually, this requirement allows you to prove the Gauss-Bonnet theorem in Lorentzian spacetime. If you are not familiar with Gauss-Bonnet theorem, it's just the theorem that if you integrate over spatial curvature or scalar curvature in 2 dimensions, you get a topological term, which is proportional to your Euler characteristic. Okay, so for continuous spacetimes, it will be described by the genus of your spacetime. In discrete spacetime, I mean, we've seen this Euler characteristics actually also in Professor Valentin's lectures, which has a relation between the vertices, the faces, and the edges, and so on and so forth. Okay, and so it's a very nice paper here, and also it's a very nice description to understand Lorentzian curvatures. And so, yeah, to give you an intuition, so if you think about, let's say this is my Lorentzian 2-dimension. So here, maybe this region, I call it, it's a space-like region, and there's a time-like region. If I have vectors in this region, space-like regions, I can describe vectors as boosting from, let's say, x1 to x2, and I can describe the angles just by using the cosh. If you describe the boost, you can do this. But for example, if I want to describe the angles between, let's say, x1 and x3, I have to cross the light cone. And as maybe most of you might know, there is no boost parameter to translate this vector to this vector smoothly. You have to cross this light cone. And so, but the way to go about this is you can somehow analytically continue by crossing this light cone. But with this, you have to make a choice of some branch cuts. And you can do this quite nicely if you make consistently all your choices, then you can describe the angles between this, like say the time-like region and a space-like region. And here I give the formula. So you see that the angles, you pick up like a pi I/2 term, which is a complex term, which is because you analytically continue this. And so that's why that's what happens here. And yeah, using the same principle, you can describe, for example, angles between 2 space-like regions which are separated by a light cone. So, yeah, so you can do the same. So you pick up a pi item, and you can think of it as because you cross 2 light rays. So you pick up pi/2 and another pi/2 term, and yeah, and so on and so forth. And actually, so you can see here, it looks like you have to consider Lorentzian angles are a bit complicated. You have to consider them case by case. But you can actually summarize all these into one formula by using what actually this is known as the geometric product, which is just a combination of the inner products and the wedge products between vectors, and then you can describe angles with this, but you have to make a choice of roots and some complex numbers consistently. Okay, so maybe as an exercise for you, the first exercise, maybe you can check that using these angles, it satisfies the additivity. So in the sense that if I compute the angle between this x1 and x2 and x1 and x3, and x2 and x3, it amounts to the angle between x1 and x3. So just use the formulas here and try and check this activity. So that's the first exercise for you. Okay. Okay, so moving on, let's move on to triangle inequalities. So also in Euclidean spacetime, we have a notion of triangle inequalities that if you have a triangle, then the length of one side cannot be greater. It's less than or equal to, so it cannot be greater than the sum of the lengths of the 2 sides. So this is the Euclidean inequality. And this follows from the mathematical inequality known as the Cauchy-Schwarz inequality. So it turns out that in for Lorentzian triangles, there are different cases, and actually similar, a similar formula is this. So if I have all space-like edges, so yeah, maybe I should have mentioned. So here we consider space-like edges to have that the square, if you compute the square length, it's positive. And for time-like edges, the square length is negative. So this is just a convention, but So yeah, so if you have space-like edges, then you don't have the Cauchy-Schwarz inequality, but you have the reversed version. So which says that the length of one edge is actually greater than the sum of the length of two edges. So for example, if I have this picture here, the length of this edge will be greater than the sum of the length of these two edges. Okay, and so if you think about it, here I put the light cone structures at the vertices so that you can have an intuition of how this works. And so usually the longer the length with the, or the edge with the largest length is opposite the vertex, which has two light cones, which are inside the triangle. And these vertices, I don't put the light cone structures, but you can think of the light cone structures as outside. So there is no light ray inside the triangle based on this vertex. Okay, so you can also build many other triangles. You can have a triangle with space-like, combination of space-like and time-like. And for that, actually you have no restriction on the edges. So basically there are no triangle inequalities. And this is also quite useful because then you don't have to check this if you have in your numerical codes, basically. Okay, so another exercise I just wrote down for you is that, okay, maybe you can also build a triangle with all time-like edges. And if you can think about what conditions the time-like triangle will have, then that would be nice. Okay, so so as a generalization, you can generalize this to higher dimension. As a generalization, this actually, it's not none other than having that if you write down a metric for your simplex, these conditions are just pointing to the fact that your metric have the right signature. So in Euclidean, you would, if you have a triangle or a higher simplex in Euclidean, you want the metric to have signature plus, 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 and this amounts to having all eigenvalues positive. Okay, and this is really the triangle inequalities for in higher dimension simplices. And for Lorentzian too, you want minus plus plus plus. Yeah, so there's a nice connection between these two. Okay, so the point I want to make here is that, so if you're doing numerics, you have to make sure, you have to check these triangle inequalities at every point in all the simplices, just to make sure that you are considering the right configurations or the right set of variables. Okay, and okay, so more on Lorentzian triangles. So here too, I just show that there are many simplices one can, or configurations one can build from Lorentzian, just learning about this triangle inequalities we described before. So for example, I mean, I have these three pictures here. So you can imagine this is 4 triangles, which are glued together and they have an inner vertex here. And all these lengths, I choose them to be space-like. So you can think of these lengths as space-like. And so due to the triangle inequalities, this D, the edge with length D should be greater than, I choose it to be greater than this, the sum of these two. And so you have a light cone structure here. And likewise, in this triangle too, it's the same. So here, I mean, just based on the light cone structures, you can tell which lengths are bigger and smaller. But the point is that, yeah, you can build triangulations like this. You can also build triangulations like this and like this. But what I want to point out to you here is that you see that in these triangles, in these triangulations or configurations, this the inner vertex here has different number of light rays or cones which are appearing. So for the first picture, you have 4 light rays, or you can think of them as 2 light cones. And yeah, and this is what we mean by regular. So I have a definition there: triangulations will be regular if every bulk vertex has exactly 2 light cones, which is what you would expect in Lorentzian geometry. Okay, but there is nothing that forbids us from building triangulations like this. So I have this triangulation that this, so it's the space, so all edges are space-like. So I have 2 light cones here inside, and the same triangulation, a similar triangle So if you count the number of light cones, there are 4 of them, which is more. And similarly here too, you have 3 light cones. So these type of configurations appear. There's nothing that forbids them, and we term these triangulations irregular triangulations because they have irregular light cone structures. Okay, and it turns out that these are related to topology changes. So if you study, I'll give at the end, if you study these 2 literatures, there's a discussion of how topology change appear from examples from these configurations. And there are 2 types of topology changes. The first one is trouser-like, and the second is YAML-like. So it depends on the number of. So I can also build a triangulation where there are even no light cones at an inner vertex, and this is usually described by the trouser-like. And these are usually, if you describe the path integral, they're usually suppressed. And the YAML configurations these are examples of YAML configurations. Sometimes these are enhanced in your path integral. And so the point is that these configurations can appear in your triangulation. And so there's a question here that should we allow these configurations? Should we sum over them? What are the effects of allowing these triangulations in your path integral? And so far in spin forms, we don't have an answer to these questions yet. But in effective spin forms, you can, because the amplitudes are simple, you can try and address these type of questions here. Okay. And so here I show you briefly what Hal described about the action of Reggie Calculus. So here you see, I show you the length version and the area version. So in the length version, I included a boundary term, which maybe didn't appear in the house term, but usually the boundary term also has the same structure. It's a sum of the areas. So this is only in 4 dimensions. Sum of the areas multiplied by the extrinsic curvatures of these boundary triangles. And how you define the extrinsic curvatures is similar to how you define the intrinsic curvatures, but just that instead of having the flat value here, you can have a half flat value. But this actually depends on the number of components that are connected to this boundary triangle also. And yeah, so the area version, you can do this by just inverting the length for the areas and computing the action here. But then we saw that the equations of motion differ, right? So in the length version, the equations of motion are given by a combination of the deficit angles and some derivatives. And in the area version, you have that the deficit angles are all vanishing, so which means you have flatness. And so there's a reason for this. And the reason for this is that usually if you have a triangulation, there are more area variables than length variables. And so these area variables they are somehow stronger. I mean, I put this in inverted commas, it depends on what you mean, but it just means that because there are more area variables, they are more free. And then to describe somehow GR, you have to impose some constraints. So this is the reason why you have to impose constraints on just to relax this condition. And so yeah, I mean, I put these 2 comments here, that the power of Reggie Calculus, actually, you can think of them as you can actually derive all the boundary and corner terms of your GR action just by studying Reggie Calculus. So it's very powerful in that sense. And like I described before, the regular and irregular configurations that appear that's already been shown by Raphael that for irregular configurations, you find that the Lorentzian action is also complex. So it comes with some I terms, and the trouser-like and the YAML-like configurations come with like a different choice of roots. Okay, so so going back to so this point that so the flatness are due to allowing more area variables, and so to relax this condition, you have to impose some constraints. And these constraints has already been also described. We see that the constraints should usually happen between two simplices which are sharing a tetrahedron. So you want to make sure that the shared tetrahedron, they have matching geometry, basically. Okay, and so we can add these constraints to the action. And so this is the form of the constraints. I mean, you have, maybe if you want to read this carefully, there's a constraint. So there are two constraints per tetrahedron. That's why you have the EI. So I runs from 1 to 2. And they are based on a shared tetrahedron. So the same tau is for tetrahedron. And sigma is two simplices. So I have a pair of simplices. And I want to make sure that the tetrahedron match. Okay. And so yeah, so maybe just as a summary a bit. So far we have seen that we want to sum over, we have seen that, yeah, area variables are natural appearing when you want to describe LQG and other fields, but we want to allow discrete eigenvalues for these area variables, and we want to sum over them in our path integral. And in addition, we also want to constrain this set of variables in such a way that you have a consistent length assignment. And so there is this tension that you always have to face. But so to do this, we have to impose the constraints. But we've seen that the constraints are already second class. And as Hal mentioned, also that these second class constraints cannot be imposed strongly in the quantum theory. Actually, if you try to do that, you get some Diophantine equations. It leads to some Diophantine equations, which you basically get no solution or very minimal solutions. And even the minimal solutions would be for very symmetric triangulations or configurations. Okay, so yeah, so with these ingredients, the strategy for our dynamics is to weaken these constraints. And the point of weakening these constraints is to allow for enough configurations which will allow you to your action to be stationary, for you to get enough variables to describe stationarity, and also to describe the weakening constraints, we will use the uncertainty relationship, the uncertainty relation coming from the Poisson bracket between the constraint as a guide. And this has already shown to give some promising results for numeric. And also, if you, in EPRL or FK models, which are other spinform models, it's a similar strategy they use by weakening constraints using coherent states and other forms. So, I mean, if you look at this picture, the blue picture describes the constraints which we approximate by Gaussians. So we use Gaussians in effective spinforms, and you can think of these, the red and the green points are oscillations of your action. And so basically you want to have enough oscillations under this blue Gaussian, just enough to describe, to have enough configurations to sum over in your path integral. Okay, so maybe the main question here is that, is there a guiding principle as to how one can impose these constraints weakly? And the answer is, I don't think we know yet. Actually, this is also related to a flatness problem in spinforms. And because this is the first mention of flatness problem here, maybe I can see a few ways what it means. Maybe naively you can think of the flatness problem in spinforms is the fact that if you consider configurations in spinforms, if you consider the path integral, then the configurations which come with curvature, which means the curvature not vanishing, are usually suppressed in this path integral. And so it's just to say that spinform somehow favors only flat configuration. So this is just a naive description of the flatness problem, but I'll mention it later again. Okay. Okay, so I showed the summary slide from Hal, and also maybe the slide I had in the beginning. So this is the effective spinform partition function that we are interested in and we want to work with. And by now we know how all these terms appear. So the measure term for numerics, so far we fixed them to be 1, but but if you want to describe some higher simplices, you will need a way to fix these, and there are already discussions going on about how to do this. And we've seen the area Reggie Calculus and these triangle inequalities, and also maybe the one thing we've not seen explicitly is how these G constraint terms are imposed. And here I just give, so the constraint terms we actually approach, how I mentioned there, you can derive them from the coherent states, but in the numerics, we approximate these coherent states by Gaussian, which is specified by the constraints, and the width of the Gaussian or the variance is described by the uncertainty relations, which we saw that it's proportional to gamma times the volume term. So these are the constraints you have. And this, yeah. Okay, so we have basically all the ingredients. And the point is that these, if you combine this, then it results in a very numerically efficient model. So you can actually try and study a lot of features of spin forms. And I put this here. So also you expect that this describe reasonable spin forms describes all reasonable spin forms in the large J regime in the sense that there are already articles showing that the asymptotic limit of spin forms, in the asymptotic limit of spin forms, Regi action appears. And so you expect that these would describe spin forms in the large J regime. And here, for those of you maybe who were present at yesterday's panel discussion, there was also one point about that we should study the universal features of spin forms. And so use simple models to describe universal features. And then this will maybe help to understand how spin forms or how spin form works, or even how quantum gravity in general, the aspects we have to focus on, basically. And so motivated by that, you can see that, okay, so this already contains many features of you would want in your quantum gravity, which are maybe motivated from LQG and spin forms and stuff like that, in particular the discrete areas and the weakening constraints. And so having a simplified model can help you to study some effects from these models. Okay. So also, there are many interesting and open questions that one can ask. So if you have your favorite question, you can probably try and study them with these effective models. So for example, I mentioned a few here. So should we sum over regular and irregular light cone structures? So allow topology changes basically, and what are the effects? And also, I mean, so far we describe space-like, time-like areas, but you can also allow null areas. In the classical action, these are vanishing, but in the path integral, you can allow this, and then fluctuations around null triangles and see what. So maybe I will describe a bit briefly this, but so yeah, so there are many questions one can ask. Okay, so far, before we go to the numerics, so I just want to mention, so far, we have studied this on maybe 3 particular triangulations. So there is a triangulation with a bulk area. Usually can build this with 3 simplices. There's also a triangulation with a bulk edge with 6 simplices, and we have a triangulation with an inner vertex. So this will be necessary for discussing diffeomorphisms and coarse graining and stuff like that, but it's still a work in progress. So today I'll show you some results from these 2 configurations, both in Lorentzian and Euclidean signature. And this is basically to test the weak implementation of the constraints, in particular, I mean, with this bulk area term configuration, and also equations of motion, because you have a bulk edge here. Okay, and so maybe the preliminary results is that, or there's some expectations is that, so yeah, if we study this for the Euclidean model, in particular this example, it indicates some resolution of the flatness problem, that curvature can be, you get reasonable semi-classical regimes for which allows curvature in the path integral. Okay, so basically here we will study expectation value of observables, and this is how you define the expectation value of observables. You insert an observable inside your partition function here, and you divide by the partition function. Yeah, so here I omitted some. So I set the measure term to 1, and I maybe imagine the triangle inequalities are already satisfied, so that's why you don't see them here. But in principle, you should put them all here. Okay. Okay, so here I show you the first picture of the numerical results. I mean, you see all these nice colors and nice graph. So this is what you should expect from these effective spin form models. So so the first plot I'm showing here is just the absolute value of the partition function. And the partition function, yeah, you as you saw them, it's a combination of the constraints and the Regi action term, and also the triangle inequalities. So if you compute, so this actually is an example which I picked from the configuration with the bulk area. And we will go through some of the features you see here. So you see this nice feature of like, okay, initially there's a sharp drop from, so here I'm plotting the partition function as a function of the Barberi-Merzi parameter, the gamma parameter, which describes the spectral gap. And you see there's a sharp drop here. And then also there are all these maxima. And how do we understand these from, or how can you explain these? So, so maybe for the first part, this is it's a feature of the model that for always there's a sharp drop, and it's actually intensified if you have a configuration with a larger curvature. So if you have a larger curvature, it drops close to 0. And this if it drops to 0, it can be bad for your partition for your expectation values, because then the partition function is almost 0. But I mean, even if it's very small but non-zero, then it doesn't really matter, right? Because you do this, you sum over this and then divide by this, so you might still get some reasonable results. And yeah, and the fact that these are intensified for large curvature is actually indicative of the flatness problem, which I have mentioned already. So yeah, so the fact that you would think that, okay, the partition function might suppress these curve configurations if you have large curvature, because the partition function is almost 0. And there's an explanation for this, but then you see that if you see the interplay between the G factors at the constraints and the discrete sums, and also the you see that, so I'm zooming in for one of the graphs here at close to maybe a region here. I mean, here I plot a large range of gamma values, which usually we are interested in a small region here. So here I show you, I zoom into this side. So here you see this interplay between all these terms. You see there's an oscillation between here. So it drops pretty close to 0. So here you see 10 to the power minus 10, but it doesn't get to 0, right? So it allows for you to still get some reasonable results for expectation values. But then these maxima can already be seen as leading to some jumps in the expectation value. So I will show a bit more detail in the next slide. Okay, and you can actually deem this as largely due to some resonance effects. And maybe another thing is like these maxima, you can see here, actually this happens very far away from small gamma, but still we can explain these. And this actually arises from some pseudo-stationary points from doing like considering the discrete sum of areas. So because we use discrete areas, so here I show you a plot of, so the blue one, which is very thick, it's the partition function. I'm sorry, it's the oscillation, the oscillatory term, which is exponential of the Regi action plotted against gamma. Sorry, I did not put this. Maybe I'll fix this before I put the slides online. Yeah, if you plot this as a continuous function, you get this, and this is the Gaussian term. Okay, but instead, if you do sum over, if you use discrete areas, then this is the discrete plot you get. And you see it's the same graph, but then you see this maxima just from using the discrete sum. And that's actually what explains this maximum here. And in the bulk area triangle, you can actually also already find a condition for where you get these. And the condition is that the Barbero-Mazzi parameter times the deficit angle should be a function of, should be equivalent to 2 pi times some integer. And actually this has already been derived by Mushin and other people also in other spin forms. Okay, so this is just to give you an overview of what's coming next. So I have more nice pictures here. And this is a result of from studying the bulk the bulk length configuration. And so here, I mean, there are so many features from this graph. I might not cover all, but already we saw this sharp drop close to 0 from the previous one. And this is a feature in almost all the numerical results you get. And also this maxima, you also see them here, but you see that this maxima actually appears much earlier. And so here I plot for gamma between 0 and 3. So it already appears quite early, which is also interesting. And here, yeah, so I'm not giving much detail, but I'm giving overview. So if you have any questions, you can always ask if you wanna understand this maybe more. But yeah, as also how mentioned, maybe if you want to learn more about this, you can join the tutorials later on. So the point here is that, so if you look at, maybe if we zoom into this section a bit, you also see the oscillations that I described before in the previous example. And also here we see a change of ordering for different scales. So these scales, the gamma scale, you think of them as representing your boundary values. So if I have a configuration where the boundary area is 100 and the boundary area is maybe 20 times that, yeah, 10 times that, 40 times that. So this is just the scale here is just for the boundary scale. Okay, so the point here I plot, so this is the partition function and it has similar features we saw before. And here I show you the expectation value for maybe computing one of the bulk areas. And here, and I divide by the classical value. So you would expect that in the semi-classical, you get 1, like it should be pretty close to 1. And you see here in this regime up to maybe gamma equal to 0.5 for maybe the red curve, which is for lambda equal to 10, you get like a pretty good, yeah, you get a pretty good line, which is good for you, right? Because this is what you want. And also these oscillations, already we explained them, but then there are also these crazy things happening, which needs more study. I think we can explain this if you probe the numerics more. And it looks like also there are different regions, and I'm sure all this can be explained. But the point I want to make here is that so we get very good results, which is independent of scale. For example, in this regime, for gamma less than maybe 0.2, it's even better for if you have a larger curvature. Okay, and also depending on the curvature on scale, even you can go as far as 0.4 or 0.6. And here the peaks, so this is for the bulk configuration. You can also explain the peaks due to the stationarity of using the discrete values areas, as I mentioned before. But here it's difficult to get a condition on these areas because you don't have just one bulk triangle, but you have several of them. So it has to be a combination of these. Okay, I show you even more. I see. I show you even more of this.
So there are 9 more minutes left. So if you want to
okay, sure.
questions or so, just
okay. Yeah, I'll just do this briefly. Yeah. So even if I consider a larger curvature, so here you also see that I get a very good regime for smaller gamma range. The gamma range is now smaller, but it still looks pretty good. Okay, so here, maybe I'll just go through this very quickly, and then so yeah, I mentioned already in the Laurentian one that you can also study how fluctuations around null triangles, and this is what we did. If you can check this paper for even more examples. And if you allow fluctuations around null triangles, then you have a choice. You can, because irregularities can appear by summing over both space-like and time-like. And if you can choose to sum over irregularities or not. And I show you here a plot for if you choose to sum over all the irregular configurations, you find that, oh, actually these take over your path integral, right? And so at first sight, you think that, okay, if I sum over the irregularities, they are bad. And this appear because in the irregular configurations there, I mentioned before that there's a complex term that come from your action, and this somehow take over the path integral, basically. And so your expectations values start to run already with gamma going up. But then if we drop this irregular configuration part and just focused on the section that's regular, which is the time-like sector in this example we considered, then you get a pretty good semi-classical regime. So here, because we're summing over around the null triangle, you expect that these expectations values are close to 0. And this is what you see. If, as I go higher in scale, I'm approaching 0. So which is good. So yeah, so here the summary is that we get a surprising good result even for null areas and large curvature, which was also quite surprising. So yeah, so effective spin forms can test a lot, as you can see. And so the summary is that by leveraging all the parameters, the curvature, the spectral gap, and also the boundary areas, which you can think of the lattice constants, you can play around with these models and then try and explain or answer questions about quantum gravity. And from these results, we see that you can already resolve some long-standing problem. And so here, I just pose a question that we see that the irregular configuration somehow dominates the path integral. And should we sum over this? Should we not? I think it's a question for us all. So maybe I see I have only 5 minutes, maybe 2 minutes. So there's a crucial question of how we can understand the continuum limits of these models. So how does, for example, the weak imposition of constraints behave under coarse graining? And so this is kind of, so to maybe the first steps to answer this question, to study the continuum limits, there's already a paper by Bianca on this. And yeah, so how we understand this is by going to, if you consider wavelengths of your gravitational excitations, which is much higher than the lattice constants, then so to do this, to study this, then you require like to have a large lattice. Okay, so you have many building blocks, then you can study the effect of the continuum limits. But this is very expensive to do non-perturbatively. And currently, actually, this is inaccessible. I mean, I showed you results for 6, maybe up to 6 triangular simplices glued together. But if you want to have like big lattice, that's almost impossible. So to answer this question, we have to seek some, go to the perturbative expansion. And here, yeah, so even at the perturbative expansion, there are already some promising results. And the fact is that, yeah, you can get linearized GR from doing the perturbative expansion. You get linearized GR plus some corrections, and this correction term scales in some lattice constant to the power, maybe I say here alpha, and you expect that alpha is positive, just so that if you take the lattice limit going to 0, it's reasonable. Okay. And the result is that if you study this using the area version of the Reggie Calculus we did on a hypercubic lattice, using the perturbations, the perturbative expansions, you get the Einstein-Hilbert term, which is can be discretized by the length Regi action, plus some correction, which is of order lambda to the 4 in lattice constants, which is pretty good. So this first step of trying to understand the continuum limit already give some promising results that in the continuum limit we might get GR because the corrections are very small. And even if you include the constraints, you also get pretty small corrections in lattice constants. Okay, so maybe I end here, and if there are any questions, I can take.
Okay.
Yeah.
Thank you very much. That was a very interesting talk. Yeah, are there any questions? So at the moment I have nothing in the chat and there are no raised hands. Let's maybe wait.
So maybe then I can just say this. So the summary is that, I mean, so we've seen effective spin forms. They capture some key features of quantum geometry and quantum gravity. In particular, if you use discrete area and then if you impose these constraints weakly, you can do many tests. And I already showed you some numerical tests at some different levels. And so if you want to study other questions, like for example, some of orientations, degenerate geometries, and I mean, if you want to do this, you can use these effective spin forms to study this because, and one reason is because they are very numerically efficient. And so here I just want to advertise that the fact that we have a numerically efficient model, it helps to address some of these questions even to some effective level, even if it's not, you don't know, yeah, you can still try and understand some physics using these effective spin forms. Okay, thank you.
Yeah, okay. Thank you too. There are still no questions in the chat.
Okay.
Yeah, but
I might have a question, but it might be a slightly more related to Carlos' talk, so I'm willing to wait. But so is it fine to ask? Or
yes, I think it's fine.
okay, so I mean, Seth and Hal might have answered some of this question, but I'll ask anyway. So I mean, for the situation that Carlo posed, the transition from a black hole to a white hole. So I'd like to talk about the Riemannian metric, just so to discuss. I think would be using something. So as we're approaching high curvature with near the trapped horizon, not event horizon, or the singularity, we're using an effective model to derive some metric in some continuum limit, I suppose that. So is that true? So if we're describing a spherically symmetric black hole, so would be something like Schwarzschild but corrected, that gets rid of the singularity somehow. And once we transition to a white hole, we just use a completely different metric and just patch it. So the same metric can't give us something that can describe a black hole and a white hole. So I guess there are two parts to my question. Are we using some semi-classical limit to derive a metric very close to a region with high curvature where quantum effects become prominent? And then once that transition happened to a white hole, do we just use a completely different metric? It's not the same metric. We just we say it's a different patch, and here is our new metric that describes a white hole. Is this true? I hope I was coherent enough to.
Al, do you want to answer?
I mean, you can start. I'm happy. It's a little bit more directed at your talk. Why don't you start and I can fill in?
So if I get your question correctly, the physics is a bit complex here. So let me just do one version of it.
Yes.
before so the picture we want to give is the following. Before the high curvature region, we expect classical general relativity to hold. So we expect the metric to be a standard pseudo-Riemannian metric of GR and solve the Einstein equations first. After the transition, the tunneling sort of, we expect the same. So a classical metric, a pseudo-Riemannian metric in GR, a solution of Einstein equations.
Sufficiently away from the white hole, I suppose.
No, deep inside the white hole.
Oh, okay.
No, we're talking deep inside the white hole and deep inside the black hole. Most of the black hole and most of the white hole are classical. It's just only near the singularity that you expect quantum.
Okay, yes.
Now, furthermore, we expect more. That as out away from the black hole, there is a classical metric that satisfies the Einstein equations. Okay. Furthermore, we expect even more. That these three metrics that I've mentioned, so inside the black hole, outside, and inside the white hole, are all connected by classical GR, and all the entire thing together is a solution of Einstein equation. Okay, so you may say, well, wait a moment, that's counterintuitive. Is it possible? And the answer is possible. It's technically possible. There is a solution of Einstein equation that does that. So at this point, there's only a region. A space-time region sort of around the singularity, but which also leaks out of the horizon a little bit, which is not a solution of Einstein equations. Okay? This is the part where we expect quantum gravity to come in, only in this part. And this is the part which has been described, if you want, intuitively as a sum over geometries like Hall is doing and sets are doing. So it might be approximated with an effective metric that does not solve the Einstein equations, like in tunneling. If you have if you remember tunneling, and when you go through a potential barrier, you can think that there is a trajectory that sort of tunnels. But what really is going on is that this quantum spread, and then you go back to a classical approximation again. So you might think that you measure the particle one side of the wall, you measure the particle the other side of the wall, and in between you treat classical quantum mechanically. So the quantum theory is used to describe this finite in time and finite in space region where we're doing the sum of a geometry. How we're doing the sum of geometry in the way the sets and Al are describing by using a spin form. Is that a partial solution to your question?
Yes.
I think I can add one more comment, Rashid. I don't know whether you have a conceptual confusion or not. You may not at all. But in the phrasing of your question, you said high curvature near the singularity and high curvature near the trapping horizon or the horizon. But the horizon in general is not high curvature. Yeah. The horizon, we could all be crossing a trapping.
I was going to say it might depend on the size of the black hole, but maybe, yeah. Okay.
So there was an important point that Carlo laid out in his talk very clearly, which is there is a high curvature regime of the horizon, but it's only very, very late in the evaporation. It's only when the black hole has become very small, as you said, that the near horizon region is high curvature. And so, as Carlo's laying out, you don't need any quantum gravity. Presumably, you don't need any quantum gravity until late in the evolution of the black hole.
Okay. Thanks.
And as you said, near the singularity, of course.
Okay.
Deepak, did we lose your question?
No, I guess I lost it. So for these spin-form calculations, the intertwiners you're using, they are the Levin speciale intertwiners, right, for tetrahedra?
So in the computations that we've done so far, we actually don't use intertwiners because we approximate them by these Gaussians that both Seth and I mentioned. So the only input we're really using is the non-commutation, which is setting the width of our Gaussian. But if you wanted to do a more rigorously exact treatment, we're making an approximation at that step, then yes, I agree. You would use Levene Speziale or any of the family of intertwiners to get a more quantum mechanically motivated shape for that gluing constraint.
Oh, I see. Okay.
Yeah.
Because my question was that has anybody thought about using like the UN intertwiners? But I guess if you have not used intertwiners at all, then that's not something that anybody's doing right now. So.
I agree. I mean, I think we stressed this throughout, but we could have stressed it even more. There's 100 open questions here. You know, there's 3 papers on this topic, and there's just so many things that all sorts of people could try in terms of, you know, pushing this to a slightly in different directions.
I have a general question, sort of. So when we are constructing these spin forms, and we are gluing together these simplices, how do you know that there are no gaps? How do you know that this is a, you know, perfect tessellation of some 3-dimensional or 4-dimensional manifold without any places where, you know, the simplex doesn't reach, right? So for example, if you perform a tiling of 3-dimensional space with let's say spheres, right? You can have a certain packing fraction which is less than 1. Similarly, in this case, like I mean, maybe it's trivially obvious, I don't know, because they are simplices or something like that.
I would say they are more, like you can think of them as the approximations, right? So approximations to some continuum thing. So if you think of a sphere, maybe you can triangulate with triangles. You can use many things, and but the point is that you glue these simplices around a shared tetrahedron, and that constitutes like a smooth gluing for your space-time. And so there may be some regions where some curvatures are concentrated, and this is what maybe Reggie tried to describe with these.
No, Seth, I understand that. I mean, I don't think that you understood my question, which is that, you know, if you just consider a close packing, right? So you consider a close packing of 3-dimensional space with tetrahedra. Right? Now you cannot take any arbitrary set of tetrahedra and construct a tiling in which there are no gaps. You understand?
So, Deepak, I think I understand the question, but let me probe. You sound almost like you're working with a background geometry picture in mind. So we have some background geometry and we try and fill it up. And that's not what we're doing at all. There is no background. There is only the simplicial triangulation, and we're studying the evolution of that simplicial triangulation. So there's no gaps simply because there's nowhere to be gaps. The variables of the theory are describing the triangulation that we built.
No, I understand that perspective. I mean, like, but you know, if I again just think about starting from a classical system, which is some close packing of some manifold with some tetrahedra, okay, classical tetrahedra, right? Then in the general case, I would get like gaps. I would get defects. Right now, one could consider quantizing.
I don't understand why.
Well, because all the tetrahedra would not necessarily, like, they would not match together to completely fill the 3-dimensional volume.
Only if they have not much boundaries, but this have much.
No, I mean if they have to. There's only a certain sets of tetrahedra which do completely tile. So it's a tiling problem. Right?
I don't get it. What is the tiling problem here?
Tiling is that, so for example, if you take a plane, a flat surface, right?
Yeah, let's do it in 2-dimensional, which is easier.
And I give you like some triangles or squares, right? So can you glue them together
Yes.
repeatedly?
Yes.
No, but
It's not a
not
plane
with
anymore. It's curved. You get something curved. That's the point. You get a gap if you pretend it is flat. But if it's not flat, you can glue them, and that just take triangle, you glue them, and you get something all curved. That's the point.
Oh, I see. Okay.
You can view it
Yeah,
the
I
other
see.
way around. I mean, consider a curved 2-dimensional thing, and just throw a bunch of point and connect it with line to make triangles. And the only constraints you have on the length, of course, is that adjacent triangles have the same side, same length, and that the length, and then these are triangles. So the length satisfy the triangle inequality per triangle.
Right,
but otherwise, you just have and if you don't need to embed it in a larger space, you just have a 2-dimensional arbitrary curved surface, which as a 2-dimensional closed surface is well defined.
Right. Okay, no, I see. Okay. No, thanks for clarifying. Yeah,
Okay.
Okay.
This is Regi, in fact. It's
There's one more question in the chat, and we should probably move on with the questions. That is, what is the interplay between effective spinform models and IR finite models, like those with quantum groups? Could similar techniques to those of effective spinform be used to understand universal aspects of IR finite models? And does this even make sense given that the quantum groups cut off large J?
So Seth, maybe I can comment on part of this, and then maybe you could talk about renormalization. Yes, there is something like a quantum group model here. The references that we listed so far don't discuss this, but we actually wrote, it's Seth, Bianca, and I again wrote a paper on area Reggie calculus that lays this out a little. You work, instead of working with flat tetrahedra or flat 4 simplices to build up a manifold, you can work with constant curvature building blocks. So you could think of a constant curvature tetrahedron and a constant curvature 4 simplex. These are perfectly well defined. You just take vertices in the constant curvature space and connect them by geodesics, and you have a constant curvature simplex. So you can write down area Reggie calculus for those constant curvature piecewise flat manifolds, piecewise constant curvature manifolds, and you can build them up into triangulations, and you could pursue all the things that we pursued here in that context. And the expectation, although we have not done this, the expectation would be that this should be related to the quantum groups that show up in these constant curvature geometries. So this is something that I've worked on also with Aldo Riello, Mushin Han, and Wojciech Kamiński, where you can study, the spin foam of a constant curvature simplex and look at the semi-classical regime and all these sorts of things. So I think this is a really good idea that you're posing here, and it's something that could definitely be pursued. It's not something we've done yet, but you're rightly pointing out that it would be a good thing to do if you are interested in IR finiteness of the model and in thinking about renormalization. So maybe Seth, you might want to say a little bit more about renormalization.
But yeah, maybe not much, but so yeah, you can try and study renormalization using maybe coarse graining techniques and stuff like that, which we do. And then maybe, yeah, so the hope is that this will touch with the infrared finite models. And maybe the interesting question one would want to get there is to have some sort of maybe approximate diffeomorphism symmetry at these infrared regimes. And so this is still an open question for now, but it's interesting to study this. So yeah, using effective spinforms, we can try and probe this, but yeah, maybe the numerics might be heavy if you try and go to do these randomizations because you need more larger and larger simplices and configurations like that. But in principle, yes, you can
Can I have a
try
comment?
and
No, sorry. I also share the same feeling. I mean, it's the quantum group version of these things. I instinctively find it more interesting. The reason I'm not working on it is too hard, because working with quantum group is more complicated. You need to learn more mathematics, and calculations are more hard. The reason I find it more interesting are two. One is that at least in some version, the amplitude would be truly finite, both in the ultraviolet and the infrared, as Hal mentioned. And in fact, in 4 dimensions, both Euclidean and Lorentzian, there are also a couple of old results, one by Mushin and one by, oh, help me, Hal.
Fairbairn.
Fairbairn and we forgot her name, woman. It's gonna, Kathleen, it's gonna come back. Moisberger.
Moisberger, yeah.
Moisberger and Fairbairn, in which they define a quantum group version of an amplitude, and they prove that the amplitude is finite. Both Mushin and they're slightly different. I'm not sure they're the same version, but it's so. But the second reason, which is stronger, is that the good reason to believe that a quantum group just reproduces a cosmological constant, the classical limit. One reason is that if you do this rather simply in 3 dimensions, it works bingo. So you replace SU2 with a Q-deformed version of SU2, and you have an argument that gives the classical limit being the Einstein equation is a cosmological constant. And my way, I think that the best way of viewing the cosmological constant is as an actual fundamental parameter in the theory. And this would be, so in a sense, it would be catching two birds with the same stone, you know, because the sort of the Planck scale works non-perturbatively automatically as an ultraviolet cutoff, and the Q deformation works automatically as an infrared cutoff. And the way it works is that, at least in some version, the representations of the Q deformed group are very much like the representation of the Lie group, but with some parameter have a maximum J, and this maximum J is sort of the maximum size. That's where the ultraviolet cutoff come in. So the theory, if the theory is defined in this way, the theory has sort of 2 constants, or at least the ratio between 2 constants, a large number in its definition, which is a large number, which is a ratio of the Planck scale to the cosmological constant scale. So this is very beautiful. I mean, it's if I was a much better mathematician, I would look at this much more carefully. So I'm not. So if somebody, and it's not a direction has been explored enough. And the local geometry, it's beautifully analyzed in this set of paper, Hal, that you were saying. So it's nice from the point of view of the local geometry. It's nice from the point of view of the convergence. It's nice from the point of view of the sort of interpretation of the constant and general relativity. It's just hard.
If I can build on what Carlo was just saying, I agree with what he said on both counts. I think it's personally more interesting to me, and also very difficult. But I think there's also a nice connection to a broader theme from the school, which is that you've heard several presentations on these corner symmetry algebras and trying to think deeply about the symmetry and conservation laws in general relativity. And these quantum groups come into that story in a very nice way. Certainly in 3D, the symmetry algebra of what's going on in 3D and the quantum groups are intimately related and beautifully connected. So I think that there's there's a lot of potential in that direction, and I just agree with Carlo. It takes some real legwork to pick up all the all the pieces.
I think we should stop at this point. So there are no more questions in the chat, and I think we're now far enough over time. So thank you, Hal and Seth, again for your nice talk and for the discussion afterwards. And
Thank you. A big thank you to the organizers. It's been a wonderful school so far.
Yes, thank you.
Thank you, everybody.
Thank you for the answers.
See you tomorrow for the last day of lecture.
Thanks. Thank you very much.